So our next speaker is Pedram Roushan from Google Quantum AI, and he'll be speaking on novel quantum dynamics with superconducting qubits.
Thank you. I'm fully wired. It's a bit hard. Anyways, yeah, it's a great pleasure to be here, and I'm very honored and thankful for this invitation. So let's get started to talk about maybe a little industrial perspective on how these things are done in an industrial setting. I prepared this slide, but now I think I learned a few minutes ago that I did not get the history correct, but probably I can be forgiven for that. But so I think the quantum mechanics have been with us for 100 years. And about 4 decades ago, many people, among them Feynman, came up with the notion of quantum simulation. This can be translated into modern language, or the language that we can speak now or we think about now, that can we control the quantum degrees of a many-body quantum system. This is not the language he used, but that's I think, the way I at least understand it. And that has led in the past few decades to lots of hardware platform developments for quantum simulation, which with the same goal, they are unified under this same goal. To be a little more precise, we can think about the specific problems that can be done with few tens of qubits. This paradigm is different from the paradigm of error correction, which I will not be talking about, and that is when you are putting hundreds of qubits together to make a logical qubit which you can error correct. This quantum simulation idea is talking about having a few tens of qubits, but they are very, very high quality. One axis is linear, the other axis, vertical axis, is getting exponentially harder as you go up. And the claim is that if you could get the control of this group of qubits, then probably you can do problems that are interesting. And not surprisingly, the first easiest problems come to be problems that are abstract and just leverage quantum dynamics without having any practical use to it, such as the Google Quantum Supremacy Experiment 2019. And then the problems on non-equilibrium dynamic comes to horizon, and if you get more and more qubit, probably you can do quantum chemistry and whatnot. And this has been guiding us in a sense through the experiments that we have done over the past decade or so. There is a group of experiments that may seem random to you, but does not look random to us, because they have been all selected under the criteria of, is there anything interesting that can be done that was not known before? In fact, sometimes internally we call it the Dasarma criteria. It's very simple to say and is very clearly guiding us. So I would not have time to cover all this, but the common theme that I would go through some of this selective work is that quantum simulators are very provide clear advantages and have been part of the research dialogue in non-equilibrium physics, maybe new phases of matter away from equilibrium, and with also helping us with understanding and doing things about low energy excitations on the ground state problems that are interesting to us. And the experiment I have chosen has meant to amplify this picture. In fact, to make it more precise, we came up with a term which is similar to neutrino being a small neutrons. We came up with this term called discoverino. And the notion of discoverino is that you will be doing small discoveries with these platforms, that it could have been done otherwise, but it just happened that you have done it with this platform first. The analogy is that in late 1800s, many wealthy people from Britain would go to around Paris, and they would use these hot air balloons to discover new lands around Paris. Of course, after they discover that, you would have realized that you could have just simply walked in there. And that's like using a theoretical method or numerical method. But it just happened that you got there with quantum processor. An example that I would use to amplify this point is this example I call KPZ experiment, and by describing that, you understand where this discovery is coming from. So imagine you want to understand dynamic under the Heisenberg model. Usually you could cool down the ground state of a system that has the Heisenberg model in it, is described by the Heisenberg interactions. Or you can do introduce a sequence of gates the way we do it. And this will be very closely following the terms in the Heisenberg model that you're familiar with. You can have the swap term, which is similar to this hopping term in here. And then there would be delta and the interaction term, which we can again tune it, and it has the same analogy. So we break down the dynamic in 2-qubit gates, and then we're going to apply this sequence of gates repeatedly, one after another, and this is going to be the Floquet version of this. But the point is that in many of these interesting physics problems, regardless of the symmetry is what matters, and you don't need to stay close to Hamiltonian, and Floquet systems should show the same properties. In this very simple experiment, we chose to do is create an imbalance initially, create a bunch of qubits excited on one side and a bunch of them to be pointing down initially. And then we ask a very simple question. How many excitation has crossed the center line? So you choose a parameter called mu. This tells you with what probability excite qubits on the left and with what probability to excite or not excite qubits on the right. And after you set that, you just start counting the number of excitation that cross the middle line. The total number of excitation is conserved, so you can just keep track of it. It doesn't matter, you say how many yellow cross this way or how many blues cross that way. And here I'm showing you a couple of examples. When mu is infinity, you can see at time equals to 0, the 23 qubits are all yellow, the other 23 qubits are all blue. And as time goes by, I'm showing you instances of how this distribution look like. We can measure this distribution with 100 kilohertz, so we are collecting this data with 100 kilohertz rate, and I'm showing you instances of what I see at every instance of time. And when mu gets smaller, you can see at its initial times that the contrast between left part of the chain and right part of the chain is about to vanish, but still you can see some difference, and you can chase this dynamic to a longer times. And then after you repeat the experiment over and over again, you ask how many times it crossed the center. This question of measuring transfer magnetization would lead to a distribution. That evolves as a function of time, but there is a probability distribution which we can measure. And we are going to analyze this probability distribution, but you might ask why we are so much interested in this. There has been a conjecture that the dynamic under this Heisenberg model fall under the KPZ universality class. This is a surprise conjecture because KPZ is written in 1986 to explain the growth of interfaces and has been successful to grow the interfaces in classical systems. And when essentially there's a diffusion equation and it's added nonlinearity and a stochastic term, noise term, and essentially it tells you that there is a correlation length and whatnot. If you look at this simple Tetris model, you can look at how correlation grows in time and how in space and whatnot. And what are these exponents? There are predictions under the universality, KPZ universality class. But the conjecture we are caring about in here is that this transferred magnetization, which I introduced, follows closely or falls into the same stochastic variable, falls same universality class as this relative height at the center. Put it simply, if you measure the snow accumulation on a ceiling and subtract the asymptotic values at the edge of the ceiling, and you look at how this middle point grows, there would be the same growth pattern and the same distribution as this transfer magnetization in a quantum system. Within the KPZ conjecture, within this universality class, there are several classes within this group, and it kind of sets by initial condition. And again, translates simply that if initial condition, initial state is sloped or flat and whatnot. And we can get to all of these questions. So I said we measure transfer magnetization, we form a probability distribution, and you can ask very simple questions about this distribution. You can ask what's the mean value and how it changes in time. You can say how's the variance of this and how it changes in time. And then you can do it for various values of mu. So far, you will see things that are very accessible to other experimentalists and other theoretical work, and you see the famous let me see, diffusive, subdiffusive, and ballistic distribution that has been extensively discussed in the literature and has been verified in the works of Emanuel Bloch's team. So we are kind of confirming each other, not a big deal so far. But the interesting physics come as a result of watching so many YouTubes looking for inspiration, that you should look at the higher moments of the distribution. And that is very interesting because it's readily accessible to us, but it's not readily accessible theoretically. And you know, there is nowhere, it's just been, people have been not thinking along these terms. But again, as I said, the data rate is very high, so you can go and do this analysis. So we are going to look at the skewness and kurtosis of the distribution that we have been measuring, and the definitions are given in here. And when you study the skewness, so this is the skewness as a function of this mu parameter and a function of time, it seems it's tend towards 0 and is not getting away from 0, which is different than the predictions of the KPZ. So, but it's hard to judge that if you give it enough time, would it get eventually away from 0 or not? Luckily, we could find a scaling function that would collapse these data, and these two non-commuting limits fall into two different edges in here. So we can again see agreement with the work of Emmanuel's team, which you can see that if you take the limit in this order, indeed, the points follow the KPZ conjecture, but if you take it the other way, it will not follow it. So one could argue that this is the correct order of the terms taking, but we don't need to go over those details and order or the validity of this scaling. But we can further analyze this data and look at the force moment of the distribution. And then you can see more clear evidence that this is not getting to the limit expected for the KPZ conjecture. So here I'm summarizing in a table what experimental values shows and what KPZ wants to show. And you can see disagreement from skewness and kurtosis, and then two other theoretical works that are also showing that I agree with one, with not agree. So a good NISQ experiment paper should end like this, saying that we found a disagreement and we don't know what the explanation is, and you let the active community in this area has pick up on it. And in fact, that has been the case. This work has been referred to later on, and this is how these NISQ experiments are contributing to our evolving knowledge of non-equilibrium quantum dynamics, and in this sense, consists an instance of discovery now. So going forward, I want to talk about maybe problems that are familiar with you, and that's starting from ground state of Hamiltonians that has been brought up, in fact, this morning. And in particular case, this is the case of TIFR model, which is exactly solvable model for 2D, is written to be solvable. And it is composed, is a grid of qubits defined in the mid of these edges of a lattice. And then the various terms are defined this way that I'm showing to you. And there is Planck operations and vortex operations. And the challenge is, can we construct the ground state? And as you can see, we have been able to do that. The reason being that this model is exactly solvable, and every term in the Hamiltonian commutes with each other, and the ground state of it can be written in a closed form in terms of these projection operators. And so therefore, it's not very surprising that we can come up with a sequence of gates to realize these quantum states. Of course, we wish to realize this as a phase of matter by cooling down, really get there. This is not the case in here. But what we are doing is we are realizing it as a quantum state, and there is advantage to doing that, as I'm about to show you, that we can do things which are typically inaccessible in a standard solid state setting. So the sequence of gates is starting from the ground state, from this product state, which are very accessible to us, allows us to get to this phase, and then basically some protocol linear in one dimension of the system allows you to make the ground state in here, and we are verifying by measuring all the local stabilizers of this stabilizer state, so we can verify that we have got it to a good fidelity. So after you develop that, you can start asking questions that has been predicted, but no one could have verified for these states experimentally, such as measuring the topological entanglement entropy. So when the ground state of a system possesses topological entanglement, means that when you go look at every patch of the group of qubits, there are two contributions to it. One is the trivial one coming from the edges of it and its boundary of it, which you have to subtract, and this complicated formula formula is meant to subtract these edge contributions, and there would be a universal contribution to it. And that's the topological one, which we try to extract. So what we could do, and then since it's a solvable model, you know the answer for each case. What you could do, you could go and start looking at these patches and start to calculate entanglement entropy for each of them. And there's lots of these patches, so you can form a histogram of them. What's the entanglement entropy for all the 2x2 sets? And what? Sorry, one case, 2x1, 3x1, and so forth, so forth. And you can have all this, and according to this formula, you can put it together. And you could arrive at the topological entanglement entropy, and you can see indeed there is -1 or log of 2, depending what community you're coming from. That is a non-trivial contribution, and that's a universal value. So doing these experiments become possible by well, the whole experiment takes maybe a few hours. Then you come to this case that you have to measure entanglement entropy of 9 qubits. One option is do you spend a week and do tomography. Another option is you get clever or you read someone clever. That suggests that you could measure by doing randomized measurement. You can avoid measuring all possible bases, and in the correlation of the bit strings that you get, you can use that to arrive to approximate the trace of rho squared with lower overhead, and that brings this experiment to about a few hours, and it becomes feasible. Because even one term is missing from this, you cannot do the summation. That's interesting. Now we can create excitations in this system. You can apply pi pulses, and every pulse creates a pair of E excitation or M excitations. And and you can get clever, but by everything comes in pair unless you get clever and start from a corner. Then you can maybe create only E or M. This E and M is borrowed from lattice gauge models. There is no significance in here. It's just a naming we give to them. And you can call one E or M. There's a flexibility in it. After you create an E and M, you can get one of them to move around the other one. So this is the ground state, and there is a protocol that moves one another one. And you get a phase accumulation, but this phase is global. So the wave function accumulates a global phase. That's kind of pointless. You cannot measure it. But what you could do, you could use what's called the Hadamard case, meaning that you can introduce a qubit outside this group of qubits and put it in superposition of 0 and 1. And then by these conditional operators on it, you can see this is a simple algebra follows from Mike and Ike textbook, that you can see this phase, global phase that was global in here become the phase accumulated on that ancillary qubit and can be measured. Using this trick, we have been able to move every particle imaginable under the sun of this model around the other one, and we can extract the associated phases and essentially make the S and T matrix or tabulate it in this table, which tells you that the E and M go around each other, and the phase accumulation, when they go, around themselves, E go around E, you get 0 phase, but these are the semionic particles, meaning when you get one E to go around one M, in that case, you would accumulate a pi phase and whatnot. And the whole excitations can be studied. Okay. That's interesting, but these are boring abelian particles. How about the non-abelian particles? It takes a little more energy to do it, but for you, we have done that too, and that's how you do it. There's maybe there's a change of basis in here from this AV and BX, BP to be on 4 X's and 4 Z's. You go to a different basis. That's maybe some technicality. That doesn't matter. But first, I want to show you what this picture that we keep seeing is, right? This is a stabilizer state, meaning that there is a group of independent observables operators that when apply on the wave function, the eigenvalue of it is +1. And this set can be very pictorially and nicely shown in this grid, right? It's a set, but we choose to show it in this very easy geometrical shape. So we can visualize it. So as I said, you can apply pi pulses, and depending on where you apply, you can create a pair of E particle or M particle. But these E and M particle, as I can say that they are like bishops in a chessboard, meaning that if bishop is confined to move on white squares, it's going to be always on white squares. And if it's confined to be moving on a dark squares, it would be always on dark squares. And if it moves, you know that your opponent is cheating on you. So there's no way you can move them around as much as you want, but if they are on the darker shades, they always stay on darker shade. If they're on the lighter shades, they would be always on the lighter shade. However, what you could do, you can deform this stabilizer set, which is geometrically showed in here. If I tell you a recipe to kind of deform this chessboard, this stabilizer set, which pictorially I'm showing it what it is in here. Now, if an excitation goes around, if it was a bishop of white squares, now it would come back as a bishop that belongs to the red one. So that's a key observation that enabled this experiment. This is the notion of the Berger vector becoming non-zero from the solid state picture of having lattice defects. This is a kind of a quantum fancy version of it. But under such deformed stabilizer sets, modify the states, now we can move the particles, and you would see now that actually the local observable would change, demonstrating the non-abelian nature of the excitations in here. So the stabilizer set, or this picture, can be kind of taken care of or be traced by noting that there is these degree 3 vortices which are effectively non-abelian excitations, and we can create them and move them and by modifying our states that we have created. This is the recipe for it. It's not really important what it is, and it just moves around. It shows you that you can move things around very nicely. So here's the actual experiments. You start with this stabilizer set without any defects, and you try creating 2 of these degree 3 vortices, and the protocol I showed you allow you to move them and spread them in a space as much as you like. You park them in this case. Next, you introduce a pair of E or M particle, however you would like to call it, and you start to move one of these E particles around this, as the way I was explaining in the chess analogy. And when you bring this one, of course, it starts to annihilate itself, or the same particle, which was not possible if this lattice was not defective. And now when you bring back these 2 degree 3 V's together, you see something quite remarkable. Now, when you do the local measurement of the stabilizer sets in here, you see a fermion in there. And that became possible because the motion was happening in these deformed stabilizer sets. So basically what I'm showing in here is that a fermion going around non-abelian particles would lead to a fermion. That's one of the fusion rules that you have to show for the non-abelian statistics. And also, if you pay attention, you would see that you can also see this key relation in here. Mainly when you start from these 2 stabilizer sets and you go backward in time in here or forward in time in here, you would see that these 2 particles could lead to nothing, lead to vacuum, or could lead to a fermion. And that's another key fusion rule signature of non-abelian particles. Okay, I think we're doing actually good in time. Let me talk about the next example I have in mind, and this is about visualizing a lattice gauge theory. So we can write down a very simple lattice gauge model, which is consistent of these familiar terms in the K-TIFR model, in fact, I mentioned. And we can just write as much as doesn't bother us, and we can handle. We can consider a local magnetic field, electric field, and we can have these matter fields interact with the gauge through gauge fields. And this would be a very ideal, the simplest lattice gauge that one can consider and study. This is a lattice gauge model because there is a local symmetry that commutes with the Hamiltonian of the system. And we can take advantage of this, and we can use that to eliminate the matter fields. And we can arrive at a matter-free, purely gauge field model, which with this Hamiltonian, these 4 terms match to the map to these 4 terms under this transformation. And in this one, you don't see local matter sites, but the presence of electric field or local or magnetic monopoles and whatnot would be reflected into and can be captured by measuring these qubits, and AV and BP violations would essentially tell you the presence of excitations and charge. So that's the concept in here. For this model, since many years ago, some of us were not even born, the phase diagram of it is known and has been predicted that there is a confined phase and a deconfined phase. And in the confined phase, the particles move as if there is a string connected with them, connecting them, and they would be their motion would be much limited. And that happens when this electric field or local magnetic field is becoming really strong, and it could happen in either directions. Okay, and in the deconfined phase, which is close to the QTIF point, the motion of the particles is not is kind of free from each other. So the first thing you would do is to make the ground state of this model. I'm not going to, so from now, just to be sure, all these four terms are non-zero, so we can safely get away from the QTIF point, which is when these two terms are absent. We have a protocol to get the ground state of this. Is a variational idea, so trust me, we can make a ground state of this model for any values. And then after you have created, you can create excitations in this. This, as I said, they come in pair. And then you can say, where do they move if I let them go evolve under the Floquet version of this Hamiltonian? And you can see in the deconfined case, these two intensity of high intensity points is spread uniformly among all the possible places that it could go in this grid. And in the case of deep into the confined case, you can see that the intensity stays together. But when you think about it, this was not a very clever choice of initial state. You know, moving and not moving, if you just let them go, even if they move, they would be oscillating maybe around the same point and whatnot. So you might need to be a little more creative with the choice of initial state. So this choice of initial state I'm showing you is kind of giving an angular momentum to initial state of the particles. Imagine that, okay, if you don't take it too literally, I can tell you that have a moon and moon going around the Earth, and the gravitational field would stop and they would just fly apart very more visibly than the case that they were stationary. And this is kind of the quantum version of that. This is the initial states. And indeed, when you look at this average separation of the particle, it becomes very more pronounced in the case that they are confined, and you see the separation is flat. Consider the case that they are not confined and the particles just fly apart from each other and the separation increases. Of course, it's a small system and they would hit the boundaries and whatnot of the system. You can analyze the same concept differently. You can say, where is my other particle when one particle is at the position of the measurement symbol? There's a 20%, 22% chance to find particle in here. And in those cases, where is the other particle? You can see in the deconfined case, when you find a particle, it's not clear where the other one is. But in the case of the confined case, when you find the other one, there is a very high intensity red spot, which tells you the other particle is also can be kind of well defined with respect to the initial one. So these are very telltale signatures of confinement. Well, as I said, when there is two particles confined, there would be a string describing that is kind of, you can imagine, or at least I'm imagining, and no one told me to stop, that there is a spring or a string that is connecting them. And we can go and actually measure this and visualize how it works. It's okay, you can think about a guitar string that's connecting these two particles, and it would be associated with this observable that we can measure. Again, you create two excitations, and then you move them to the edge of the sample, and they kind of lock them. You get them out of the dynamics. These are the two excitations, they are locked. And now you're going to look for the vibration of the string connecting them, and the quantum observable associated with it is these observables. You can see deep in the confined case, the string is kind of frozen in place. This is where you find this observable to be non-zero, and you can see as you go further in time, it doesn't do much motion. In the case of the confinement, the string is very floppy and it goes up and down, and in fact, it's very hard to even say how it is defined or whether it is. And that is what you see in here, and there's a there is an intermediate stages too and whatnot. The same physics, the same data can be done in here. If you're experimentalist, you would know that with colors we can do lots of cheating. So we always show you a cut, so you can see how data looks like when you show a cut through this data. And you can see in one case, indeed, the string goes all over the place, and the other case does not go very far from where it has begun. And this shaded region are the decoherence limit, or limit that we can resolve, because this is a very deep circuit, maybe about 800 gates or so. So there is a decoherence that comes in. But besides that, you can see that in one case is more or less it stays the same. The other case it just goes away from where it has started. If there is a string, there must be a string breaking too. And when the string breaks, there will be two particles created where the string is broken. And this is this case that we are trying to look for that after subtracting a background vacuum. So we are looking for the cases that the string is breaking, and then there is a particle created here. Again, we create a string and we stretch it up there. And if it breaks, the probability of seeing particle where the string existed initially is higher than the other places. And this is indeed what we have observed in here. The probability of finding particle on the top part of this grid is higher because the string was originally stretched to be over there. And the lower part, and the probability of finding a string in lower part is far lower. Yes, very good. So this is again the color map. So every time I show a color map, I'm feeling obligated to show you a cut through it. And you can see that in this case, when you get really to the proper limit, you can see the probability of seeing a string is far above the background, and the other case is very close to the background. And again, confirming the notion that we can see the consequence of a string breaking and particle formation at the ends of the string. Okay. Okay, let me give some concluding remark, and then I stop. The works I have shown you is the work that, in fact, I'm very proud to say these are the work of the students mainly that we have been hosting them for under the program I created called the residency program, where the student come and stay with us for a year. You can ask me about that. And this is the point, the infrastructure that my colleagues at Google put together, and the students come and benefit from that. But more significantly to me is the collaboration that we have done with academic groups over the course of the last decade. There are many, many people that we have collaborated, and in fact, one person we could not find and collaborate yet, that enable us to push this Feynman's dream to its current stage. It was a dream, and we started from few qubits and whatnot, but with the help of Google quantum infrastructure and all these talented researchers in the field, we have brought it to current stage, and I think the future is very, very interesting ahead of us. So let me make a suggestion on what to make out of the Google Willows announcement. As some of you have known, or maybe all of you know, a few weeks ago, Google made an announcement that there is a new processor. And you know, to put it simply, I think we are saying that we are not in Kansas anymore. We can talk to Toto and tell them we are not in Kansas. But the question, of course, is where are we now? You know, okay, we know where we are not, but the question is where are we? There's one obvious take on it. I think I don't need to reiterate on it. The new processor is better. We all get that, right? The new processor is better. You look at this measure matrix of fidelity. I'm comparing Willow processor with Sycamore, the older generation, and this is a vertical axis is the error rate. Sorry, is the histogram, is accumulated error rate. Yeah, well, is a histogram. Is a cumulative distribution. And then the horizontal axis is the error. And you can see is a log scale too. So you can see that the order of magnitude things are better when you think about single qubits and readout. Willow is this more darker shades, and the Sycamore is the older one, and everything is just moving to the left. You can ask for CZ gates, you can ask for C phase gates, and everything it would be looking better. So that's great news, meaning that the quantum volume that we have now accessible has increased, and we can do more more of the same, or I don't know. But that's the point. The point I'm trying to make is that this is obvious. Now the experiments can be more sophisticated. But one thing I like to say, and I've been struggling to find words not to insult anybody, is that there are things that comes to horizon that did not come to, that did not exist before. Maybe I use a prime example, which is very dear to me, and it's just collected by, in fact, a student who's coming from a theoretical background. In few hours, they can take this data very routinely. I didn't say that, but the Hamiltonian describing the dynamic in the system is the Bose-Hubbard Hamiltonian. So you can create the ground state of this Hamiltonian wherever you want, whatever range of parameter, and then you can ask how many excitations I have created. This in 2D, this Hamiltonian goes through a phase transition at J over U value of about 0.6%. So you can very easily look at the population of the doublons and whatnot you created, and you can measure this many times. But with this example, what I like to highlight is that new capabilities and new hardware tells us new ways of thinking. And sometimes I feel, I don't know, I use the phrase theoretical properties taking precedence. I'm short of words, how to say it without, yeah, it requires new ways of thinking. Such a data is very easily accessible, but you ask many people, they keep asking you about, band structure or matrix elements or something, while there is such a wealth of data comes very freely and is very suggestive of reformulating the questions and problems. Anyways, thank you.
Questions?
Pedram, thank you very much over here. Let me ask a question on the KPZ thing. Actually, it's two questions. First one applies to all of them. How does the error rate or decoherence of individual transmon affect the physics, very beautiful physics that you showed us? You're almost convincing me that you'll very soon tell me something I don't know. But but how does it affect the results? You didn't touch upon that. There must be, if your decoherence is very low, your results will not be as beautiful. So what, can you just expound on it a little bit?
Well, the way it works is that, I don't know if this is the right thing. There's calculation of it up to the point that we can do up to 18 qubits, and so we would follow, and it would be it would follow this rather well. The dominant source of error is photon loss, which we can be simply post-selected on. What I didn't tell you is that every bit strength, sure, it comes with 100 kilohertz, but 1 out of 10,000 has the correct number of excitation. 9,999 goes to trash can.
So there is a lot of post-processing that
you know for this particular problem was good selection that we could manage that.
Right.
But then this is not very difficult problem to go to. But at some point it becomes the realm of experiment, and I ask you to trust us.
No, I know, I understand. Okay. And the second question is that on the KPZ magnetism, the Heisenberg model work that you showed, very interesting stuff. Did you look at your data, whether it has intermittency or not, multifractality on those things? Because in a KPZ, we know all those results, what the structure looks like. Did you look at all?
No.
Or to higher order things, look at multifractality and so on? It may be worthwhile to do that. There may be something here that's, intermittent.
No, we didn't. Yeah, I mean, it's hard to talk about multifractality probably when you have 40.
You may not have enough data yet.
Yeah, but for 2D, that's why I'm trying to inspire everybody with my animation. We might go after such questions.
And the last thing is that why couldn't I, and I know I cannot, but I missed it. Why couldn't I take your Heisenberg model and just simulate that on my, on 24 or 26 qubits that I can do with our GPU machine?
You could. Yeah. That's the point of this slide.
Okay.
You could, but then at some point, yeah, I mean, yeah, I think the experiment was done at 46 qubits. And depends on how good your grad student is, this boundary can shift, but there would be a limit.
But I will not have any error in my simulation because I'm doing digital simulation. So that's the advantage I have over you. It will not change as I go longer and longer, right? In time.
Yes, you can go longer in time, we can go bigger in system size.
Hi, thank you for the nice talk. So in one of the slide you mentioned that we can calculate linear entropy by randomizing the measurement so that we cannot part up all the qubits and use tomography to find the linear entropy. So in a similar way, can we find the higher order any entropy like von Neumann entropy and other entropies experimentally?
Where is you? You want to take? I don't know. Well, as far as I know, the idea gives benefit only for this trace of rho squared. I haven't seen. I'm not aware of other things. For trace of rho squared can be approximated with this one. I don't know about methods for other.
Okay, so one more question is that so let's say we have multiple qubits and because of Bengaluru evolution they will start entangle among themselves. So if I given for two qubit, can we find the entanglement between these two chosen qubit, like say concurrence or something like that, directly like from this experimental point of view?
Yeah, anything that can be expressed as a Pauli operator measurements, you can measure any Pauli operator, and then you can construct density matrices and then extract negativity and concurrence and all that, yes.
Okay, okay, thank you.
To a given size.
Yeah, so hi, Pedram. So in the Fradkin-Schenker phase diagram
Yes,
that
yes.
you showed, so you showed all kinds of data on the electric strings and
Yes.
things like that. You know, so if you go back to that phase diagram, there is a very mysterious point of the phase diagram, which is where those two lines meet.
Yes.
From whatever numerics exists, it looks like it's a second order multi-critical point, but we don't have any theory for that point. So I wonder whether with your newfangled system, you can measure some things that would shed light on how to think about it.
No, we didn't think hard about that. Most of the cases I show was just line cut in here or line cut in here, very kind of a straightforward thing to, we were excited to see strings and whatnot. But if you have any clear question that can be said, given our finite sizes, these experiments have lots of ancillas in them. This is maybe 50 qubits experiments already really demanding. But yeah, we didn't look closely.
Yeah. We have lots of questions one could ask. I don't know which ones can be answered.
Yeah, good.
So for the Heisenberg model, you had calculated the integrated charge, integrated current
yes.
distribution. So using MPS calculations, Nidarich and Frozen had done this calculation using matrix product state simulation. So there we have a sense of how long it takes to, how complex that calculation is. So can you give a sense of how long it takes for you to do repeated initialization, time evolution measurement, evolve it again? What can you give a sense of?
Yeah. So the data rate is 100 kilohertz, but then 1 out of 10,000 is meaningful. So you get 100,000 data points a second, but 1 out of 1,000 or 1 out of 10,000 of the data points have the correct number of excitations in it.
100,000 time evolution till time t?
Yeah, it doesn't matter. That's really absorbed. The communication with the machine is the bottleneck. The execution of the experiments is in the megahertz. So 100 kilohertz is really the rate that data comes. Yeah.
Thanks.
Yeah, let's see if there are any online questions from people who are listening to this talk online. No. Yeah, you had a question.
Yeah, so you have a gauge theory here with matter field. So ultimately, this string breaking picture has to fail.
Sorry,
ultimately this this picture here for distinguishing the confined and deconfined phases has to stop working, right? Because of the string will break anyway,
Mhm.
since there are matter fields around.
Yes,
Is
yes.
have you thought about how you might get around that, or it's not, that's not an
Finite
issue for
size.
these
Finite size was our
rescued you?
yes. So some of these would not survive. Yes, you're
Yeah.
right.
Right. Let's thank the speaker.